Let's do the problems on our quarter exam A review worksheet. Question 1, reviewing rational functions. So we've got two types of asymptotes. Division by 0 gives us a vertical asymptote at x equals -2. Set the denominator to 0. And our horizontal asymptote as x goes to infinity, the ratio of the leading coefficients here, because the degree of the numerator is equal to the degree of the denominator. For our intercepts, we're going to find the value when y is equal to 0. We need the numerator to equal 0. So set the numerator to 0. And when we set x to 0, then we will get -1/4 for our y-intercept. Types of discontinuities, well, we have a vertical asymptote, so we've got an infinite discontinuity at the vertical asymptote. All right, in number 2, we've got a factor of x minus 3 that cancels. So here we would have a removable discontinuity and we would have a vertical asymptote. So let's go through our questions here carefully. I guess I already answered the second part. So we would have a removable discontinuity, a hole in the graph, when x is equal to 3. And then we could plug that hole by doing the limit as x goes to 3. That would be 1/6. So we could actually answer our question here. As x goes to 3, we would have 1/6. And that should be our limit for both of these. Oh, let me take that back. I'm getting ahead of myself here. I just did the limit as x goes to +3, but these two say -3. Well, let me back up. -3, this would be next to our vertical asymptote. So we better finish the question correctly here. So our infinite discontinuity is at our vertical asymptote of -3. So the question is, what happens to the left of -3? So let's look at the value as we get close to -3 from the small side. If we put in a number like -3.1, we can see that our answer will be a positive over a very tiny negative number. So it is going to go to -infinity. And our limit as x goes to -3, but from the positive side, think of putting in a number like -2.9, and then we would have a positive over a very small positive. So here it's going to go to +infinity. And we've got one more question. I have to scroll here to see what it is. The limit as x goes to infinity, we're going to get close to our horizontal asymptote. So let's go back here. When the degree of the denominator is larger, erase my writing here. When the degree of the denominator is greater, we know that y equals 0 is our horizontal asymptote. So that's our limit as x goes to infinity. All right, our next question says, from a graph of f prime, how can we tell the intervals where the original function is decreasing? So when f prime of x is less than 0, the graph of f is decreasing. So negative slopes give us a negative first derivative. From a graph of f prime, how can we tell the x values when f has a local maximum? Well, let's think of a simple example here. When f is rising and then falling. So in other words, f prime is positive and then f prime is negative. So when f prime changes from positive to negative, assuming it's continuous, so we could say at a continuous point, then f has a local maximum. From a graph of f prime, how can we tell the intervals where f is concave up? Well, let's look at my picture right here. Here we can see in this section concave up. Remember what concave up means? That the slopes are increasing, and that means that f prime would be rising. So these from the graph of f prime, so if this was our graph of f, by the way, here I don't want to confuse the issue. When the slopes of the original function are increasing, that's concave up. So when the slopes are increasing, that would mean f of x is increasing. When f of x is increasing, then f is concave up. And we could say here, since the slopes of f are increasing, you don't have to put both of these. The parentheses here is just to help clarify. All right, number 6. From a graph of f double prime, how can we tell the intervals where f is concave up? Well, that fits our definition a little bit easier when the second derivative is greater than 0. When f double prime of x is greater than 0, then f is concave up. From a graph of f prime, how can you tell the x values of inflection points? Well, let's think about it. When f prime is increasing, we have concave up, and when f prime is decreasing, we have concave down. So when f prime of x changes from increasing to decreasing, f has an inflection point. From a graph of f double prime, how do we tell when f has an inflection point? When f double prime of x changes from positive to negative, or vice versa. I guess I could have just said when it changes sign, S-I-G-N. Okay, and you don't need this parenthesis, but let's clarify. Since concavity changes, f double prime positive means concave up, f double prime negative means concave down. So when f double prime changes signs, we have an inflection point. All right, let's see if we can, given the graph of f of x, can we sketch its derivative? Well, from this point to this point, we know we've got negative slopes. So, and it's very negative. From this point to x equals 0, our graph is rising. So our slopes are very positive. And how positive? Well, it looks like maybe the slopes here are getting very close to 2. I don't know if we care specifically how high we want to go here with our slopes, but we want to get up maybe to 2. And here our graph has negative, oh, sorry, I'm forgetting my inflection point here. This is the place where we have the most positive slope. Here the slopes go back to 0. I better get in my turning point here. So if I want this to go up to 2, so I needed to get back to 0 here where we have this horizontal tangent. So how high you make this loop, I'm not too worried about. I was just guessing that the slopes maybe were about 2. And notice I was using this as the inflection point somewhere in here where the original graph has the inflection point. That is where my f prime of x has to change from increasing to decreasing. So now we've got negative slopes from here to here, and I guess I'll use this point matching as my inflection point. So I kind of have determined whatever I did in that previous loop is going to be about the same. And then here I have to get back to 0. And then from that point on, our slopes are positive. So how positive, we don't know, but if we started with a continuous smooth curve, then f prime is going to be a continuous smooth curve. So I made a bit of a mess of that, but hopefully that will be clear enough. All right, in number 10, this is now the graph of f prime. Same graph, but now it represents the derivative, and we're working backwards to say what would the graph of f look like. So now I have to read the slopes. So from here to here, the slopes of our original graph are very positive, and from here to here, our slopes are very negative. Where our first derivative changes from decreasing to increasing, f will have an inflection point. So here at 0, we're going to have another inflection point. F has an inflection point here, and f has an inflection point here. So stop and think about all of those. You can make some notes for yourself if you want to. Down here, you could say f is increasing since f prime is positive. And then we've got a short section here from here to here where f is decreasing when we get below the axis. So if this is helpful to you, and then between these two zeros, we know that f is increasing again, where f prime is below the axis, f is decreasing again. So we've got several changes here. And then where f prime is above the axis, f is increasing again. All right, well, let's see how I can draw this. We're going to start out. We don't know how high or how low we're going to make the graph, so I'm going to just pick. I can see here that we've got very positive slopes, so I could start my graph anywhere, but I know that it's going to have a turning point at each place where f prime changes and hit 0. So we're rising and then we're hitting 0. So I'm going to go up here, and then here's where we're hitting our next 0. And then here's where we're hitting our next 0. And here's where we're changing again. So why did I put the graphs up here as opposed to down here? We don't know. So as long as we end up with a graph that has the same shape when we do this antiderivative, when we're going from the derivative backwards, we're going to say antiderivative. All right, so we need an inflection point then where our first derivative hits a max or a min. So our next inflection point from concave up to concave down, somewhere in here. And then our next inflection point somewhere over here. And then our graph rises very sharply. So our original graph must be going up like this. So now exactly how high or how low you make those curves. And I think we kind of can tell where we want some symmetry. But as long as you have the inflection points and the turns. So my inflection points are here, and f has an inflection point here, and f has another inflection point here. So as long as you have a graph, I think, somewhat similar to this one. Frankly, while I'm talking and drawing those, I'm no more accurate at that than you guys might be already coming up with a better way to visualize those. All right, let's press on though so our video doesn't get too long. The limit of e to the negative x. Remember that e to the negative x is the same as 1 over e to the x. So instead of rising on the right side, it rises on the left side with y equals 0. So our key point would be at 0, 1. So know your common functions. As x goes to infinity, this limit will be 0. And our limit here as x goes to negative infinity, when our exponents become negative billion, these two terms become negligible. So these terms become negligibly small when the exponent is very negative. So we would end up with negative 3/5. And our limit as x goes to infinity on the positive side, when our exponents are positive and large, those terms get huge. So then it is these other two terms that become negligible in comparison. They're still there, of course, but when we have e to the billion over negative 2e to the billion, that is going to be very close to negative 1/2. All right, and our common function here, we've seen this so many times. I hope that we won't have any questions about this. So our limit as x goes to positive infinity is going to be positive 1. And here, this is approximately, when we have the square root of x squared, we can think of this as the limit as x goes to negative infinity of 3x over approximately the absolute value of x. So the trick here is to notice that the numerator will be negative, but the denominator will be positive. So our limit is going to be negative 3/1. And in f, we do direct substitution, we would get 0/0. So our trick was to rationalize by the conjugate, top and bottom. So these problems are always written so that something will cancel. So we'll have x plus 9 minus 9 in the numerator. And that solves our 0/0 problem, because now the x's would cancel and leave a 1 as our numerator. And now we can do direct substitution to get our limit. So our numerator is 1 and our denominator will be square root of 9 plus 3. G is some practice in factoring the difference of cubes. So our denominator, these are perfect cubes. So we come up with a trinomial. And then this factor cancels. And now we can do direct substitution. So we'd get putting 5 into our x's, we'll have 25 plus 25 plus 25. Some of these you might actually start remembering the patterns and can skip the work. The limit of cosine as x goes to infinity, well, cosine has boundaries of -1 and +1, but it never approaches it as an asymptote, so the limit does not exist. In letter I, the limit as x goes to infinity, this is a right end behavior question for a rational function. That's the horizontal asymptote. The degree of the numerator and the denominator are equal, so we would take the ratio of the leading coefficients. So in other words, y equals -5 is a horizontal asymptote, is how I'm answering that question. But -5 is the limit. And here we've got our sine of a glob over the glob. So we need to do some changing here. We're going to bring that 2 out of the denominator. And again, you can skip this work if you recall it from previous problems. What I need is to make my denominator 5x, so I have sine of a glob over the glob. So if I want to put a 5 in the denominator, I do that by putting a 5 in the numerator. But rather than putting it there, we're going to bring it out in front. So then we would have 5/2 times, and now we've got our theorem, sine of a glob over the glob, and this goes to 1. So our result would be 5/2. That's a theorem you need to remember, by the way. And I think we will do this one problem. No, I think maybe looking at the time here, I'm going to pause and we'll pick up here in part 2 of a video.